Hello and good afternoon, everybody, and welcome to another Polkadot deep dive. This week we're going to be doing a introduction to Ink, and it's the second in our Ink series. Last week we looked at the palette contracts, so today we're going to actually just start off with a quick sort of recap on palette contracts, just as a refresher. If you haven't seen that session, we highly recommend it. It's a lot of great detail in there. And then following on from that, we're then going to look at Ink and Rust and why the two work so well together. We're then going to quickly look at some contract basics to kind of prime you for our demo later by Andrew. We're then going to explore the cargo contract tool and what the different subcommands available are there. And then I'll pass it across to Andrew and Dan for two different demos. Right, let's get started. Okay, so just to recap for the session last week. So really the focus there was kind of an introduction to smart contracts generally, as well as WebAssembly. So WebAssembly, if you aren't aware, is essentially a portable compilation target. And a lot of the solution that we're presenting today, palette contracts, I think everything else is powered by WebAssembly. It's kind of a very critical piece of infrastructure. So the session last week essentially introduced WebAssembly, but it also introduced smart contracts. So if you may recall, smart contracts essentially are a abstraction layer on top of the parachain logic, as you can kind of see on the right-hand side. So the benefits of using our smart contracts is there's a lot less friction. Um, we don't have to worry about all the underlying infrastructure. As long as we've got some tokens, we can code our token and deploy it to a chain, essentially enabling permissionless deployment of our untrusted programs on a blockchain. Um, so obviously, due to that permissionless nature, the programs are untrusted. So we need to have various safeguards in place, and those range from things like fees to sandboxing, as well as revert protection. Then, in terms of the actual smart contracts palette, which we have on the left, last week's session kind of focused on the fact that this WebAssembly palette provides an execution environment for our WASM bytecode. It's designed to be programming language agnostic. As you can kind of see on the right, we've got multiple different languages which all compile down to the WebAssembly bytecode, and then the smart contracts palette actually enables the execution of our logic. Um, the goal of it is obviously to enable smart contracts on the parachain, and as I mentioned, to execute in a safe manner. And then the session also focused a lot more in terms of the actual architecture of palette contracts. And it kind of focused on the API that's made available to the smart contracts for the underlying blockchain. And it also introduced concepts of weight and gas, which is used for metering execution. And then finally, it touched on storage bloat and how we can use storage deposits, as well as uploading a single contract once and then having multiple instantiations of it to reduce on-chain storage bloat. So that's a quick recap. So now we're just going to kind of look at some of the attributes of Ink, the language itself. So Ink is a very opinionated programming language for smart contracts. That's its kind of prime focus. It's a domain-specific language which has been embedded within the Rust language, and obviously then uses the standard Rust patterns that Rust provides for us and used by traditional Rust programming. The power and simplicity of it essentially comes through the Ink attribute macros, which makes it super easy to get up and running very quickly with the actual Ink attribute macros doing all the work for us. If you aren't aware of attribute macros, essentially it's a concept of metaprogramming, whereby we can annotate our functions with a little bit of attributes, and essentially that will generate code for us. So it's code that writes code. Then, as we mentioned before, obviously Ink is very much focused towards WebAssembly, as is most of the substrate and Polkadot stack for our runtimes. And the reason for that, obviously, WebAssembly is a very established industry standard, and it gives us great portability and a lot of huge advantages by using it. Then moving on, so Ink also supports most common data types that you'd expect to find within Rust, ranging from your primitive types to things like your enums, structs, etc. And that's all made possible by the scale codec. And then finally, and perhaps most importantly, Ink is kind of native to Polkadot, so it's great to be able to write smart contracts, which we can deploy on any smart contract enabled parachain. But it's also very useful to then use that as a prototype to be able to sort of figure out what do we actually want to design, deploy it, see that it actually works in a real world scenario, and then hopefully that idea can then graduate to a parachain. So that's Inc. As an introduction. Let's briefly look at why Rust. So Rust, in the sense of the language, is type safe, memory safe, and free from undefined behaviors, which makes it very ideal for a smart contract language. We can benefit from the Rust ecosystem, so any improvements to the underlying language benefits Inc., as well as the wide uh, levels of support that are available for the Rust ecosystem as a whole. It also has great tooling, which works out of the box. So the usuals like Rust format, Clippy, and Rust Analyzer. But then also Rust provides no overhead. It's not a garbage collected language, and through the designs of the language, it can allow us to essentially generate minimal runtimes, minimal codes, which are super lightweight and very efficient. It's obviously safe and efficient, as I just mentioned, offering zero costs and safe abstractions, but also it's very productive. Through Cargo and the creator ecosystem, you can easily pull in dependencies, those especially focused towards WebAssembly, which Rust has first-class WebAssembly support. And then finally, and perhaps most importantly, for the nature of blockchains, is the small size. Rust data structures can be very compact, and that's super important for blockchain where resources are constrained. So that's a little bit about Rust. So then let's just move on to the actual prerequisites for actually getting started for using Inc. So three major components, sort of super easy to get up and running. So obviously we need Rust and Cargo. Two minor components within that is the Rust source compiler component, and then the WebAssembly target, because obviously we targeting WebAssembly, then upload and blobs onto the blockchain. The second component is the Cargo contract component, which is just a command line and utility, and that allows us to develop our smart contracts through various commands, which we'll cover in a few slides. And that can easily be installed by Cargo install once you've got step one up and running. And then the third component is the actual substrate contracts node, and really that's just the standard substrate node with the contracts palette added, as was sort of introduced to us last week. And again, it's another simple command, Cargo install, and that just brings and builds the binary for us and allows us to launch our node where we can then deploy our contract to. So it's super easy to get up and running pretty quickly. There's a link at the bottom to get more information and to be guided through those steps. So we've got an environment up and running. Now we actually want to start developing. So just to introduce some of the basics of the contract and how the different sort of components sort of fit together. So you can kind of see the overall Rust syntax there, and you can see the Inc attribute macros as I introduced earlier. So at a very high level, we're just defining a Rust module, and then we're decorating that with the Inc contracts, and that kind of acts as our entry point into the contract. Then within that, we then need to define our storage for the actual state of the contract. So in this instance, I've just called it my contract, and that's then been annotated with the Inc storage Inc storage attribute. As I mentioned, there needs to be exactly one of those in our contract. We can then add additional events if we want. You can have as many as required, depending on your use case or your logic. And those are annotated with the Inc event attribute. And then we get down to the actual implementation of the contract. So how do we define our behavior? So we define our various functions, which obviously need to be public, so that they can be callable from the outside world. But then they can also then be annotated with the different attributes depending on the use case. So Inc allows us to have multiple constructors, unlike Solidity. And the reason for that is so essentially we can deploy the contract WAS and blob once, and then we can instantiate it multiple times, potentially using different constructors, providing different values to get different functionality. Thereby essentially targeting the whole storage place idea mentioned last week and in the introduction. And then subsequent to that, we've then got the actual messages, and these are kind of the messages that get sent in and out of the contract. So these are sort of our traditional getters or setters, or accessors or mutators. So the getter would essentially return some state, or maybe do a calculation on that state and return a value. But most importantly, it isn't actually going to change any state. Or we could have a setter, which, as you can see, takes a mutable reference to the actual struct self, and that allows us to then take in some outside parameters and then to mutate the state based on those parameters. Obviously, state mutation requires writes to the chain. So in that instance, we then need to charge for that based on resource usage. It's also just to mention that there should be at least one of these messages defined for the contract based on the ENC rules. And then finally, at the bottom, we've got our tests. We can't have code without tests. There's kind of three different flavors of tests that we can write. There's the standard Rust test attribute, which just allows us to write a standard, Rust unit test. We've then got the inc test attribute, which essentially allows us to define an integration test. Now, the difference between these two is that if we're going to be using anything from the underlying blockchain environment in our code, then we need to use the integration test because we're integrating with the underlying chain in terms of functionality. So an example might be, do we need to access the caller of the contract, or do we need to check the balance? If we do anything like that, we need to use an inc test. And then finally, we've got an inc end-to-end test. And essentially that allows us to actually write tests which operate against an actual running substrate node. So as we saw in the previous slide, where we can quickly build up our substrate node, deploy a contract to it, and then run actual end-to-end tests from our terminal against the running node to make sure that the contract actually functions correctly when it's been deployed to the chain. And then finally, just to mention at the top, there is this concept of the environment trait. So by default, this section at the top, you don't need to define at all. It's optional with the default value of the default environment. And all the environment trait does is just gives you access to all the types that are exposed by the underlying chain. Those could be things like account ID, balance, hash, block number, etc. It then also provides additional access methods such as like caller, transferred value, balance, or being able to emit events. So that's kind of a sort of a quick overview of a contract. We're now going to look at the cargo contract utility, which is just a command line utility, which allows us to do a little bit more with our contracts once they've been written. So various subcommands are available. We've got cargo contract new, which just generates a starter project for us. So, scaffolds it based on the Flipper templates. We've then got check, which checks that the contract builds as WASM, but doesn't actually generate any build artifacts. So it's kind of a slight optimization if you just want to write a bit of code and then just check to see that everything works, especially in terms of building towards WASM. We've then got the build subcommand, and that does indeed output different artifacts into the target inc subdirectory. And there's kind of three different flavors there. There's the .wasm, which is the optimized WASM binary. So your contract compiled to the WASM bytecode. We've then got the metadata.json file, which is the ABI or application binary interface, and that's language agnostic. That's just a descriptor of how can your DApp user interfaces actually interact with your contract via the metadata.json file, so that you can kind of define your methods and everything else. The ABI acts as the intermediary to allow external user interfaces to be able to call into the contract. And then finally, we've got the .contract file, which is simply a bundle of the .wasm and the metadata.json files. Then just a few of the other subcommands. We've got cargo test, which just runs the test as a normal cargo test would. We've got cargo contract upload, which allows us to actually upload the compiled contract to the chain. Obviously, fees are involved in that. And most importantly as well, the actual hash of the WASM is a key piece of bit of information that essentially ties us all together, as we'll see very, very briefly in a second. We've then got instantiate. So once we've uploaded our contracts, we've got our WASM stored on chain with a hash. We can then instantiate different instances of it, as I mentioned, using different constructors if required. And then just to close off, we've also then got call. We're going to look at call very briefly on the next slide, because there's kind of two different flows that can be taken depending on the type of call that you want. If you're doing a dry run call, the idea is we're just inspecting state, so there's no transaction fees required. Whereas if we're just doing a normal call, that would be changing blockchain state, so we do require transaction fees. And then finally, decode just allows us to take some hex encoded string and to be able to decode that into some input or output using the ABI, which is defined in the metadata.json file, so that we can see it in a human readable manner. So just to briefly touch on this, so these are the various sort of keys or sections defined within the metadata file. I'm not going to go through all of them. Just the sort of high level ones is within the source one, we've got the information about the WASM and the actual hash of the WASM blob. We've then got the contract with metadata, but then also we've got the actual ABI. If you recall on the recap slide, we can have different languages that are using this metadata for these WASM contracts. So depending on the language, they're sort of free to choose how they want to describe the ABI. So in terms of Inc, we've got the spec section, which is the contract information, the storage layout, the type registry for all the types used in the contract, from primitive all the way through to complex types. And then finally, the actual version number. So currently we're on version 4. And then just to conclude, we've got the actual user, whereby you can define any additional metadata that you might want to appear in the actual ABI. So that's just a sort of quick overview on the cargo contract. From my section is just going to take you through the two different flows, whether we're doing a dry run. This was done on the previous session in a much more complex way, a much more detailed way, shall I say. Whereas here, I just want to briefly summarize it to say that if we pass in the dry run parameter, all it's going to do is it's just going to send a call to the RPC of the node using the stay call function. And then depending on the parameters that are passed in, it's going to load up the contract, execute the function, get the results, and then return the results of that to our terminal. So a very synchronous approach. As you can see, it's not expecting any state. So it's not mutating any state. So the idea is no fees are required there. If we don't choose to pass on the dry run parameter, then what it's going to do is it infers that we're actually trying to call a contract and make a state change. As part of this flow, it does still do a dry run, but that's just for gas estimation. So and that it does prompt you: do you want to do a dry run? Yes, no. If it does, it'll estimate the gas for you, and obviously those values will be passed into the gas limit below. And then we can just specify the destination address of the contract, any value to be sent in, as well as the actual data encoded that we can be calling on the contract. So the difference here is we've got our signed transaction that gets submitted to the node by RPC, which then gets included into the transaction pool. And then depending on obviously fees and demand, it will at some point get included in a block. So this is a very sort of asynchronous nature. Once you've submitted it, you just have to wait until your transaction eventually gets included, and it may not be included whatsoever. But more importantly, when it does get included, the only output from the contract or this transaction is essentially the events. So you'll see here a typical flow where we've got balances.withdraw. So the first step is, to execute the transaction is going to withdraw some fees from our balance. It's then going to call the actual transaction, the actual contract, and then it's going to actually charge the transaction fees, refunding anything that was perhaps not used. So I hope that kind of gave a bit of an overview in terms of the two different flows and when you would use the one and when you use the other one. And at this point, I'll then pass along to Andrew and Don. We're going to demo sort of creating a contract from scratch for you, and Don's going to ask some really interesting questions as Andrew gets coding. So thanks for your time, and I'll pass it across.
Fantastic. Right. Okay. So you'll see we're just going to create a basic contract and go across some of the concepts you learned in the previous slides. But instead of on slides, it will be the actual code. So here goes. We're assuming, if you're following along, we're assuming that you have installed the cargo contract tool. So it's just, if you haven't, then you can install that with cargo, install cargo contract. I already have that. So there we go. So that's what we need. I'm in a terminal here inside my IDE. So what I'm going to do is create a new contract. So this at the end is the name of it. So I'm just going to call it demo, cargo contract new demo. Right. So that's created it. Oh, hang on, I'm in the wrong place. I'm inside the wrong directory. Okay, let's try that again. Okay, so now we can see. So in the demo, right, we've got our new contract. So we're going to open this up in the IDE. Right, so here is, I'm opening up in the IDE the contract that I've just created. 2 files, can you see that all right? Dan? Is that big enough on the right side?
Okay. Can you easily make it bigger?
Yeah.
That's good. Yeah, perfect. It's good.
Good stuff. Right. Okay. So what we've got is we've got two files that's created: the cargo.toml file, which we call the manifest, and that's typical in, if you're familiar with Rust, that'll be very, very familiar to you. It's where you define all of the dependencies and some metadata about your Rust crate. So yeah, just the name, the version, etc. And this is very important. Let me zoom in. So the template has added the ink dependency for us. So yeah, we just got one crate. Well, there are three crates you need to, at the moment, you need to reference. You can see there's ink, scale, which is for encoding, and scale info, which is for metadata about types in the in your ink contract.
And also for off-chain, what is it? When you test your contract, is that true?
What, scale and scale info?
No scale info?
Yeah, I mean that is very important for interacting with your contract, because you need to know what the what types of arguments are accepted and what types of values are returned, right? But we'll get to that. But scale info is just kind of a way to describe types, essentially, and how they're encoded and decoded. So if you're using a user interface,
of course,
and in our case the command line tool, then it will know what the types are of the arguments to the functions are. Okay, so what I'm going to do now is just go through this line by line and just describe what's going on. And Dan, if whenever you have a question, just interrupt me at any time.
yes.
So at the very top, we have this attribute. So this is important because when we're compiling to WASM, we're targeting an environment where the Rust standard library is not included, right? So if you so you can't use any of the libraries that are available in the Rust. Well, we're in an environment where the Rust standard library isn't available, right? So I think that's important to understand, because it's a constrained environment. We're running inside, like we're running using a WASM interpreter inside pallet contracts. So we don't have access to the full standard library. So that's what this is here for, the no STD, and that is only enabled when the STD feature is not enabled. That's what it means. So you can see that in the manifest, we have the STD feature enabled by default. But when you're building the contract using Cargo contract, it will disable that feature and build it as a WASM blob.
That's clear.
And in fact, let's build that right away, actually. So okay, so I'm just going to demonstrate the.
Yeah, and just for clarity, like things like struct and enums, those are not from that STD crate. It's more like things like vec, right? And
yeah. So yeah, the whole Rust standard library, right? Anything that's in there. Now you can still use vec there. The way that we do that is that under the covers it uses the core library. So you can use core vec like that, right? So you can access anything that's inside the core library.
Okay.
So yeah, that's how we kind of still use some stuff that's available in the core environment. But you couldn't. But I mean, in effect, it's when you're using SCD, it's actually not core. It's alloc or something like that. But normally, if you're in an STD environment, you just, it's imported automatically. So you can't do that. You can't do that in an ink contract, but you can do this. But we have a prelude which exposes many of the common things you'd like to use, such as vec and string. So usually you'd use in our case you'd use ink, prelude, vec, right? You'd use that.
And why not just use core? Because, for example, I've seen a few contracts where they declare the public type for the result, and they get those from the core.
Yeah, you can use core. Yeah, so yeah, you can use core result.
Yeah, but is there a difference between the vec from core and the vec from prelude, or is there no vec in?
Well, I mean, not really. No, it's the same. Okay. So the ink prelude is just re-exporting the things from core and alloc. It just provides it just provides a unified interface. So there's nothing to stop you doing this. But I'm glad you brought it up, because if you're normally programming with Rust, then a common thing is you might just kind of try and use a vec somewhere as an argument, and then it will give you a compile error. You'll be like, oh well, you're not used to having to import vec explicitly. So what you can do is just say bring in the prelude like that, and that will import all of your common types like vec and string and so on and so forth.
Okay.
So what I've done there is just demonstrating how to build it. So cargo contract build, you can either build in debug mode, or in release mode. When you're compiling for to release production to a live chain, you'll always use release mode. It's not very helpful, is it? Oh, I see. Right. Okay. Yeah. It's. Just delete all of the nonsense that I've added there.
Could you maybe show how you can insert a debug print statement?
Yeah. Definitely, we can do that. Yeah, we'll just get it to compile.
And also,
first.
if you include that in your program, but you compile it with the release flag, then this will be not included. Is that true?
Yeah. So you're right. Yeah, that's an important distinction. So if you are yes, if you are using debug statements, then if you're compiling release mode, then they just won't do anything, right? So it means that you can keep the same source code for when you're developing and deploying to production. You don't need to kind of comment out your debug print lines. Well, we'll show that in a second once we get it up and running. All right, so just quickly. So let's have a look at the artifacts that were generated when I built it. So I built that one in release mode, and you can see there that the size is 1.4 kilobytes, and that is referring to the size of the WASM code here, which is demo.wasm. And yeah, I think Frank went over what those files contain. That is obviously the plain code, and the demo.json, that's the metadata, and demo.contract bundle is just is essentially the metadata, but it embeds the WASM bundle. So it's just kind of a convenience for user interfaces, just to have a single file instead of having to drag and drop two files. Excuse me, I'll just close the door very quickly.
Yeah, and then for the listeners, the WASM file is the actual code that will be stored on chain.
And I can show you where those are. They're in the target ink directory. There you go, you can see them. So if you're using the contracts UI, then you'll need to navigate to that directory. So you can see Target. Don't know whether you can see that file explorer on the left-hand side.
Yeah.
But inside Target Inc, there you go. There's those 3 files right there. So yeah, that's important to know. Yeah, if you're using, especially if you're using a user interface, you'll kind of have to use a file explorer and then navigate to this, usually this contract bundle file, and drag or drop it or open it. So that's a useful thing to know. And yeah, you can here. Let's just have a quick look. I know that Frank went over the format of the metadata file, but yeah, here it is that we've generated. So let me demonstrate something.
Yeah, and in
quick.
very simple words, if you would go to the contracts UI and you would upload your chain, the front end has some code that just reads this JSON file and then shows the user of the contracts UI, like, hey, these are the functions that you can use, and it will also decode the events for you if you execute a contract. Yeah, that's where it is for.
Correct. Yeah. And so just very quickly, so let's say let's take the constructor here. So name of it is constructor. New. Yeah, constructor. So you're using the constructor to initialize the values of the contract, and we'll talk about it more. You know what's happening in a second. But since we've got the metadata file open,
okay, yeah.
You can see that the cargo contract, the build process, has generated this metadata file, right? So, and we wanted to talk briefly about why it's important to use cargo contract build versus like you can create a command like using cargo build to build it, but cargo contract is doing a lot of other bits and pieces. The most important thing probably is it's shrinking the size of the binary to being as small as possible. So you can see the original WASM is 20.6 kilobytes, and the optimized version is 1.4 kilobytes. It just strips out all of the unnecessary stuff. So yeah, the 2 main things it does are shrink the binary as much as possible, and generate the metadata, right? So so for example, that constructor, you can see that here is the spec for the contract, and here is the list of constructors, and here is the name of the constructor new and the values, and you can see the type information here, right? So you can see that that's just describing in the metadata. There you go, the name and the value, and the type of the value that it expects, and the UI will generate an entry box for you to put in that value. In our case, the we can do it from the command line.
Yeah, because eventually then this front end will then also make an RPC call with a JSON file to send that to the node, right?
To send what to the node?
When we want to call a contract with the constructor, is it then also like in a JSON format from like, hey, we want to call? Is it also the other way around? Do you get me? So we
so it is so it uses the user interface uses the JSON file metadata in order to convert the user inputs into a I mentioned those dependencies earlier, into a scale encoded value of that type, right? So well, maybe it's better if we we can possibly do a demo. I think I can run substrate contracts node. I think I figured out to get it working. So this is the local development node mentioned by Frank in his intro. So it's running. So I've compiled my contract, And now I can instantiate it. Instantiate.
Yes, and if you instantiate it without having uploaded it, it will basically do both in once.
Yeah, that's right. Yeah, so I'm skipping in this case I'm skipping the upload step because it's
Yeah.
it will happen automatically. There is a distinction because you can upload without instantiating, but in this case, just for the demonstration, I'm going to right. So let me see. I haven't used this in a while, but let's see. So I think it defaults to constructor new, so I can just say args right false. Right. Okay. So so the SURI stands for secret URI, and that's using a built-in account, one of which is Alice, and that's pre-funded with funds on the development chain. Normally you would, I mean, this is for development purposes only, but you can at the moment you have to put in your you would have to put in your private key there, right?
Yeah, so you're using an account and you have a private key, they sign it, that's all, it's all done for you.
Well, yeah, I mean, I would say if you're using on production chain, then don't use this interface at the moment because you have to put your private key on the command line. So yes, but this is at the moment just for development purposes. Alice is a URI for a built-in account. That's the secret, or the secret key is well known. So I should be able to call this. So this is the important part. I think it defaults to new if you don't specify. Right. Okay. So there we go. Yes. Okay. It's changed the way it happened by default. Right. So args false. So by default, it's done the dry run. So let's see. I need to run execute. Run it. Okay. So now it's so this is the distinction that Frank was talking about: the dry run versus actually executing it. The default, as you can see above, was to run the dry run, and then I've added that X parameter at the end, and that said we want to execute it. And now what it's done, it's performed a dry run again to get the estimated gas limit, and now we're just going to confirm the transaction. So we can ignore all of these events for now. We're just demonstrating a success of what happens when you invert the constructor.
Yeah, is that true? By default, it does a dry run? Is that new?
Yeah,
because
it is new. Yeah, it is.
Okay.
It caught me by surprise as well.
Right.
Yeah, I mean, it's I've not used that before, but yeah, previously it was the other way around. Previously, you had to provide a dry run flag. I think that was in the presentation as well. But in the latest release, yeah, it's switched around.
Okay.
So
that's clear.
Fine. Yes, I think the original reason that I was wanting to demonstrate this was because to describe, why the metadata is, or what it's used for, right? So essentially, in this, the type information is to understand that it can interpret the argument that I provide as a Boolean and encode it as a Boolean. So otherwise, it doesn't.
That's clear.
Yeah. Okay. So fine. And then when you get to your part, you can explain what all of that means. So how long do I have left? Just so I know how to pace it.
Where's the time? 15 minutes, but yeah, 15 minutes. Take the 15 minutes, and I'll take the rest if people would like to. So let's just focus on you, and then.
Sure. Okay. Fine. Right. So let's resume just to going through the contract line by line to see what's going on. So this is probably the most important line in the whole contract, because this is the macro, which is essentially reading everything that's happening inside this module and generating all of the, well, you can ignore the test for now, and generating all of the necessary code, the boilerplate code to hook in with the pallet contracts. And it's the essence of Ink is just to that the logic is stands on its own. You don't need to write a lot of glue code and wiring code. The macro is generating everything, not everything, but everything which is not to do with the business logic for you. So yeah, this is the main macro that you need, and it's doing all of the parsing of all the code in here, and then all of the expansion.
Could you maybe give one example by showing the default environment? So the environment trait, and as default, we have the default environment implemented for contracts.
All right. Oh, so you mean actually just talking about the configuration?
Yeah, just showing what that gives to the environment of the contract. So then we can use the public type balance and hash.
Oh, right.
So what happens under the hood?
Okay, right. So
just
you want
showing
me to,
the environment. Oh, yeah, that's also cool. Yeah, so what Andrew uses here now is cargo expand, and it basically spits out the Rust code with all the macros expanded to. So everything that happens under the hood will be now visible as well. Damn, that's a lot, yeah.
Yeah,
yeah. So I think just the first 10 lines are a good example. Yeah, it's a lot, but I think the first 10 lines are a very good example. What, for example, this Ink contract macro does.
Yeah. So even just the volume of code is a good demonstration, because you can see that there's not very much code here, but under the covers, it's just generating a bunch of stuff, right? You can see all of the bits and pieces, but specifically what you were talking about was these types that we have available in the environment. So these type aliases. So these are the typical, the common types that you would use when writing a contract. Count ID, balance being probably the two most common ones that we care about. Those are, because we're dealing with substrate, those are configurable on a chain by chain basis. They could be different in different blockchains, and that's why we have this environment trait that allows you to configure these types. If you don't specify your own environment, then it will use the default environment. Like Dan said, you can just say and this might not work because I don't have so, but if I had defined my own environment, it would substitute it in that place in the it would simply oh, there you go. In fact, it's done it. There you go. MV equals -1. So you can see how changing something in the affects the
in the expanded version
generated code.
So and this makes it easier for developers for example, taking arguments for functions where they can just easily say balance, and they don't have to worry about declaring this whole balance type and giving that a value or a type.
So you can just do
yes, exactly.
But all of those types are available in the context, which is one of the slightly unintuitive things about Ink, because if you're like a Rust developer, even if you know about macros, you're like, okay, well, here is this balance type, like where is it defined? I don't see it, and your IDE will not be very particularly helpful unless it does good macro expansion. But that's where it comes from is here, right? So all of these type aliases are in scope inside your contract, so you can just use them. So wherever you see a count ID balance, then that's what it is. Okay, well let's get going through. So first thing we have here is this storage struct. So when you call a constructor, you need to initialize the values. You need to initialize the storage struct. And so that is what persists state between calls, and it goes directly into the database on the substrate node. We don't need to go into how the keys are generated for that. I think it's good enough to understand that when you construct it, you have to kind of set initial values, and then whatever's returned from the constructor is in the background is stored into it generates a key from that, and then it stores the serialized or encoded values into storage, right? So that when you call a contract, those values are loaded up from storage and are available to mutate or to read from. So here's an example. So after you've initialized, so when you're calling the message, in the background, this storage struct instance gets loaded in from storage and then gets passed into your message, right? So now you have the available that value. In this case, we can write to it because we've got this mutable keyword here. So we can just set the value to be something different. So we're just assigning it to be its opposite. And then in the background, once if it's a success and the message finishes executing, then the whole of the storage struct in this case is written back into storage, right? So you can start to see something that is happening automatically generated by Ink, is that prior to the message being invoked, it loads the state from storage, and then it passes it into the message and allows you to modify it. And prior to it being invoked, then it can write the modified value back into storage.
Yeah.
If we didn't have Ink and you were just writing using plain Rust, then you would have to kind of write all of that code yourself. So that that's kind of the value proposition of Ink versus, because of course you can target palette contracts with just plain Rust, but you have to write all of the code yourself.
Yeah.
Okay, so carrying on, we've got a second constructor. That's just demonstrating that you can have multiple constructors. So like we just talked about, messages are the most common entry point into an Ink smart contract. Your constructor you just call once. Messages are the main way to interact. Like I said,
can you show the payable what is it, attribute?
It can be. So there are various various different configurations or different things you can configure on the message attribute. One of which is marking it as payable, which means it can you can, along with the when you submit a transaction, you can send some value of the native token along with it, and the contract account will receive that amount into their account. There are a few others. I think the most interesting one, or one of the most interesting ones, is the selector. So you can usually the selector is kind of the how Ink in the decides which message you intend to invoke, right? It's not just the name of the function. It's derived from the name of the function usually, but you can override that in the selector attribute. So
where would that be useful for? Because eventually every account is unique. So because you're hitting a unique account of a contract, and then you assume that of course there's not two functions with the same name. So just
it's useful. A trivial use is if I kind of do some refactoring in my contract and I change I changed the name to Flip2. And if somebody's built a user interface which kind of has the selectors or the metadata hard-coded in the interface, then it will continue to work because you've selector is common and static. And I think there are some kind of standards like some of the ERC standards, for example, have their selectors are, I think, defined. Well, they're not defined, but in order to be, say, compatible with an ERC standard, Ethereum selectors are generated similarly from the names of the functions, but it's not using the same derivation as Inc uses. So in order to provide an interface which is ERC compatible, then the custom selectors are useful in that case, because otherwise you would have to kind of try and reverse engineer some function name that resulted in the you'd have to kind of brute force it to find a name that resulted in the selector which was compatible with the ERC standard. Does that make sense?
Yeah.
So I think that's its most important use cases for like interlanguage compatibility, because Pallet Contracts is a multi-language platform. So you can have a contract compiled in Solidity that will that wants to call an Inc contract, and vice versa. But in the case of Solidity to Inc, in order for it to invoke a specific message on an Inc contract, then it could either, if you have a custom selector, it's easy to do because you can just look it up. And so that's the main use case, I would say.
Yeah, that's clear. Yeah, so let me suggest something. I'll just now quickly go through the ERC20, and I have two things that I would like to show. Please go if some of the presenters have to go, because it's Friday and it's end of the day. So, but Fee, if you can switch to me now. Yes. So what I'm now having in front of me is the ERC20, the famous ERC20 token. This has, here we have the struct. So this is the storage of the contract, where we have the total supply. Here you can see the balance. Mapping, this will be left for next Inc presentation, where we go in depth into storage, but it basically stores all the accounts that have a certain balance of this ERC20 token, and allowances is something specific to this contract as well, where you can approve another account to spend or transfer your tokens. What we haven't covered with Andrew is the Inc event, which is interesting. So if we go, for example, to the transfer, the constructor, so creating a new ERC20 token, we basically initialize the balances field. We insert the owner of this ERC20 token into this balances, but before we return the actual, we emit an event. And what is important is, if someone requests to execute a smart contract, this eventually will be executed by all the nodes of the blockchain. So it doesn't make sense to return whether this actual execution succeeded or not. So this in whole substrate is done through events, where this is basically added in each block. So in order to also see whether your execution succeeded, most of the applications do this for you, but they'll just query the next blocks and see which events were added, and then see whether your event, which relates to your transaction, happened or not. And something that I wasn't sure of, and maybe you can confirm, Andrew, but so there is still this return value in a message function. So yeah, here. So this is the transfer message. So to transfer tokens to someone else, but it still returns a result. And I wasn't sure why this is useful, but someone on Stack Exchange answered it because if you, for example, make a cross contract call to this contract, then you want to know immediately whether it succeeded, yes or not. Is that the reason? Because
Yeah. Yeah. So I mean, if there's some, well, there are two. If you throw an error, if you return an error from the message, then it will revert the contract, right? So the execution won't succeed. But if it's been invoked by another contract, then it will the calling contract has the opportunity to handle the error, right, and do something about it, right? So it doesn't have to stop execution. So if contract A is invoking contract B and contract B returns an error as a result, then contract A can kind of handle that error and choose to continue execution and kind of but if the transfer has been invoked directly from a transaction, if you're invoking directly contract B, then it will just revert the state. It won't succeed.
Yeah.
Right. So
yeah, exactly.
So that's the distinction. So yeah, I guess it's useful to and also to encode errors. Although you'll lose the value if you're just invoking it from a transaction directly. Yeah. So it's mostly for cross contract calls, I would say.
Okay, cool. And then something else. Yes. So here we saw, or Andrew showed us that we have we can use types like account ID and balance, but we also have access to who calls the contract, so which is done by this function, the caller. But we can also let's see if that is used in this. No, but there are some functions. Well, I can just go to. Sorry. Damn. So we have access to the caller of the contract. We have access to the amount that is transferred when this contract was called, and this is in combination with the payable attribute that Andrew just showed us. So then we can see, hey, how much did this caller, how much tokens did it send in combination with executing this message of the contract. Way to fee. There's a bunch of functions. Block timestamp so that you can do something with time in your contract. Account ID, which contract is actually called. So this whole environment gives us access to a lot of useful information and makes it also a lot easier to program with Ink smart contracts. We're already over time. Is there someone maybe with a very urgent question? Now we have Andrew on the line. Otherwise, no. Should I just quickly show how to deploy and call, or should we leave it?
Go for it. Do it quickly. Yeah. Wow.
Okay. So I think we already have the contract built. Yes. So here on the right, I have my contract node, which I'm gonna run now. Yes. So first we instantiate it with Alice, and we have to give an argument, which is the total supply in this case. So we now uploaded it and instantiated it. The reason why I don't have to set the execute flag, which, so I have the older version, so the default is not the dry run. The code hash, this is basically the address of where the code is stored. Is that true, Andrew?
It is it's literally the code hash. So it's the hash of the code file, but that is used to retrieve it from storage, right? So if you had to compile
Okay.
a code and run
Yeah.
run I think it's Blake 2 over it, and that will give you that code hash. And then so when you're instantiating, you provide the code hash as an argument to say, and then the contracts node will use that to retrieve the code blob from storage, or to so that it's kind of used for the key to retrieve the code from storage.
Yeah. All right, and then we have the contract account ID. Also, a fun fact: like a contract is basically has an account ID similar to a user. So also, for example, if you would have contracts on, let's say Polkadot, which is not the case, but contracts and accounts could just natively transfer Polkadot tokens to each other. And that's also what the payable attribute does, literally. So let's give an example of Astar. You call contract a message on Astar with the payable message. You base the user basically transferred also Astar tokens to the contract, and the contract has the account ID behind it. Yes? Am I still? I'm not saying incorrect stuff here, Andrew? No,
Sounds
I
good.
assume no. Okay, so just stop talking down and just show some stuff. So we instantiated it, contract, and now we're gonna call the contract. So we copy this bad boy, and then we call the message where we're gonna, let's say, transfer, and Alice is gonna be the caller, where I copied or I saved Bob's account ID, and we're gonna send him 500 tokens. Boom, that all succeeded. And then we can see that if we do contract,
have a look. You can see the contract emitted, the event that was emitted by the contract itself, right there in the
so that's this one.
inside,
yes, yeah, exactly.
data, yeah.
So here you can see the emitted event where we sent from, which is Alice in this case, to Bob with a value. Also an interesting thing to show. Sorry, everyone. But you can see topics within an event, and these topics help people to get information from the chain, from events in an easier manner. So those topics are basically, maybe you can explain that, Andrew.
So think of it like indexing, right? So in this case, you've transferred to Bob, right? And so we're indexed by uses his account ID as the topic, right? So if you're kind of looking at all events that are emitted on a blockchain, you might want to say, well, I'm only interested in transfer events that are sent to Bob, right? So think of it like a filter or an index. So instead of having to kind of read every single transfer event and inspect it, you just look at the you look for the topic with Bob's account ID, where it appears for transfer events, And then so you're filtering only and then you only need to download and decode the events that well, you only need to decode the events that you're interested in, right? So it's just a way of filtering, indexing events, because if you got a busy chain, lots of stuff going on,
it makes
or
it
for
easier.
for block explorers, right? Think of your Etherscan or whatever, for a lot of their stuff, for like ERC20s and stuff, if you wanted to, a lot of their views, I guess they're using events to generate, so I guess they're using topics to to look at, to kind of build their database, to display the events.
And you need to be careful because there are a max amount of topics that you can pinpoint in one of your events. That is also so you can see here max event topics is in default environment set to 4. You can change that as well, but yeah, you need to be careful for that, probably because it takes more storage of data.
Well, the reason that's constrained is because the contracts palette itself will reject any more than 4 topics, I think, by default. Yeah, so it's configurable so your node will be configurable to have a maximum amount of topics. I guess it's taking up computation and storage resources, so it's limited on the node, and then it's limited on the Inc side in order to prevent you from, in the first place, creating too many topics.
Yeah. All right. So, and as like giving the value a topic, it doesn't make sense to search for a transfer of 10 tokens, because it happens a lot, but a transfer from Andrew to Dan, that is more specific.
So anything, if you have like if you have a database, it doesn't make sense to have an index on the balance value column, right? Because it's that's inefficient. But if you so think of it like a database index, whereas it does make sense to index on account ID. Well, not always, but in this case, yes. So
yeah. All right, and then to finish it off, I'll just show you that this call, what I just did, worked, where I do a contract call to our ERC20 contract. And in this case, I want to see the balance of Bob, where I need to copy his account ID again. And in this case, we do want to do a dry run. And then you can see that Bob has 500. If we do this for, well, no, I don't have Alice account ID. So, but if we do a total supply, let's do one more total supply, and then I will give everyone we can total supply. Oh, it doesn't have arguments. Yes, so the total supply is 1,000. Yeah, so this is how you interact with your contract. You can also do it through the contract UI, of course, which is a lot easier.
Well, I mean, it depends whether you're a command line interface aficionado or user interface. Okay. Yeah, but there's both options, right? It's it depends what you prefer, right? Some people use only Git on the command line, and some people use Git user interfaces. So it's kind of, we want to provide options that are whatever your preference is.
Yeah, and there's also Polkadot.js, of course, which you can also use.
Yes. So
yeah, and then one last thing and that is just because we have a running node running already, is how you do the end-to-end test, which basically mimics everything regarding deploying your contracts and, well, how your end-to-end tests are specified. So you can literally mimic deploying and interacting with your contract. You need a running node for that in the background. And that will, yeah, you do that like this, all the tests. This is not important. So yeah, I just wanted to show that. All right. I think we're there. These errors are not errors of the tests, but not important. All right, we're done. Sorry. I hope we gave some good information to you guys. Other than that, I think,
Cool. Thank you.
Thank
you.
Nice weekend,
Thank you.
everyone. Yes. All right. Thank you very much, Andrew.
Thank
and
you,
Frank.
Dan. Thank you, Frank.
All right.
Have a good weekend.
Bye-bye.